In this video, you'll be introduced to the Big Bang, regardless of the fact that you take a Regents exam or that this will be on our next test. This topic explores the origins of our universe. And as new discoveries and theories are made, and as you get older, you will now have a basis of understanding about how human beings were able to conclude the starting point for all the matter, energy, and time that make up our universe. Let's get started. So when we talk about the Big Bang, of course we're not talking about the TV show. We're talking about the beginning of the universe, the moment when everything was created. One essential question is, if the Big Bang was the beginning of everything, then a good question might be, when was the Big Bang? When did that happen? The concluded date of the most recent Big Bang event is something like 13 billion years ago. This is a theoretical time. Obviously, there's some interpretation where this could be incorrect, but this is the time when we believe that all the matter and energy in the universe was created. That number, 13.7, where did they get that from? It could be 20.7. It could be 1,001.7 billion years. Where did they come up with that? In order to tell that story, we need to go back to 1927. This is George Lemaitre. He was a Catholic priest, an astronomer, a cosmologist, and a physics professor working in a Belgian university around the turn of the century. He lived from 1894 to 1966, and in 1927, Lemaitre published an unnoticed paper about how the universe was expanding. And at one time, it must have been smaller in the past. And it wasn't until 3 years after he published that paper, in 1930, that leading scientists in the field, like Albert Einstein and other world-renowned astronomers, took notice of his work, and a lot of astronomers still claim that he revolutionized the study of cosmology, which means the study of galaxies and distant objects. But it wasn't only Lemaitre. There were other scientists looking for clues about the origins of our universe, and here's one. This is Edwin Hubble, an American astronomer who lived from 1889 to 1953, and he spent a lot of time studying distant galaxies as well. He also concluded that the universe was expanding, and for his work, they named the Hubble Space Telescope after him. So what Hubble was doing was, he was in Washington, the state Washington, at the top of Mount Wilson, using a large telescope, and looking at pictures of distant galaxies. Actually, at that time, they didn't even know galaxies existed. They were actually looking at nebula, which later on they concluded were galaxies. And in 1929, Hubble reached a discovery or a conclusion that these nebula, these galaxies, were actually moving away from us. And if they're moving away from us, that was the proof he needed to say, well, the universe is expanding. So how did he make that discovery? That's one thing we need to discuss. This is a spectroscope. All right, it's a very simple device. At one end, there's a narrow slit. At the other end, you can look through it, and you direct it towards a light source, and the incoming light through the slit is broken into the colors of visible light. So you'd basically see something like this. All right, all the colors in white light, or the colors of visible light, are shown. And if you were to look at a fluorescent light bulb or even the sun, this is what would be produced. This is a continuous spectrum, which means there's no interruptions, no black lines, no breaks in the colors. And the shorter wavelengths are on the right here. Notice the smaller number 4. That represents a shorter wavelength, and that's the color violet, the color blue. On the other side, we have longer wavelengths, which is the color red. Right? That number 7 represents longer wavelengths, and that's what we talked about when we discussed the electromagnetic spectrum. If you were to use a spectroscope and look at a gas tube of hydrogen, A gas tube of hydrogen is hydrogen gas, which is colorless. You can't see it. Contained in a glass tube, and that glass tube is heated up with an electric current, and the electric current excites the gas particles, and they glow like this, right? That nice reddish pink color, that glow, is the result of an excited bunch of particles of hydrogen gas. Anyway, using a spectroscope, we don't get a continuous spectrum. We actually get something called an emission spectrum, and without getting into the details of what that is, it's a result of a gas being heated up. So in an emission spectra, you have a couple of vertical lines. In this case, there are 5 vertical lines. There are 3 towards the left, and then there's one all the way on the right, so to speak, which is the red line. And that's indicative of hydrogen. That's like a standard. We can compare things to that because on Earth, that's what hydrogen looks like using a spectroscope. Okay, stay with me because this will make sense, I hope, when I show you this next part. So this is what it looks like in a laboratory on Earth, right? If I looked at hydrogen in a laboratory on Earth using a spectroscope, this is what I would see. Now, if I looked at that same gas hydrogen in a distant galaxy, I may see this. A subtle difference, but those 5 vertical lines are shifted to the right. Here's another galaxy. They're shifted even further to the right. And then finally, our third galaxy, Galaxy C, the lines are the furthest out of the 3 galaxies. So what does this mean? This shift to the right demonstrates that these galaxies are moving away from us because they're shifted towards the longer wavelength, which is red light. And the hydrogen that's in these galaxies, when we look at them, what we see is that that spectrum is pushed to the right or to the red side, and as a result, that's our evidence that that galaxy is moving away from us. And it turns out Galaxy C, because the lines are pushed furthest to the right, that one's moving the fastest. So the further they are to the right, the faster something's moving away. So this is really what, Lemaitre and Hubble did. They provided these clues in this system to really show that the universe is expanding because the galaxies are mostly moving away from us. When we see distant galaxies and we use spectrometers, they're moving away. And Hubble went on to actually categorize what this meant. He says a redshift is the result of a change in wavelength as a galaxy or star moves away from Earth. So if something's redshifted, that's telling you it's moving away from us. And on the opposite side, a blue shift is the result of something moving towards us. It basically would look like this. So here's a redshift, okay, of this star. If you watch here, changing the speed, you can see how the spectrum of the star, depending on how fast it's moving away from us, is shifting it to the right. All right, the spectral lines are being pushed to the right because it's moving away from us, and therefore it demonstrates a shift in the spectrum. And a blue shift is the opposite. So instead of it moving away from us, it's moving towards us. And again, the speed is the one that really determines how shifted they are. But basically now they're moving to the left. Okay? And that shift, either red shift or blue shift, is the result of something we already talked about. You may be thinking about it. You may not. But it's because of the Doppler effect. If you remember, when we looked at the Doppler effect in a previous video, I gave an example of a light emitting object changing its position and producing on one side violet light or blue light and on the other side red light because of the change in the wavelengths. So the Big Bang theory is that all matter, energy, and space were created from a tiny point of light like this, and instantaneously all that energy was released to create matter and energy. Where does that theory come from? Well, if you think about hitting the rewind button on your DVR and going backwards, right? You go back to the beginning. If everything's expanding today, then at one time in the past, that means that they must have all been together. If they're separating now, then if I rewound time, if I actually hit the cosmic rewind button, everything would go back into this tiny point, which we now call a singularity. So if I rewound the Big Bang, I'd be back here. So that's where this Big Bang theory really comes from. And because we can keep track of the speed of light and the rate at which galaxies are moving away from us, or in general, that's where we got the number 13.7, because we can use that information to calculate the time it's taken the universe to get to its current point. There is some other evidence, really notably one other piece of evidence that you should be aware of, that helps us understand the Big Bang, and it's called cosmic background radiation. Cosmic background radiation is electromagnetic radiation that fills the universe. Now, we can't see it and we can't detect it. If you were to look through a telescope or even a spectroscope, you would never be able to see it. It's in an electromagnetic wave called a microwave, and you can only detect it using a type of telescope called a radio telescope. Anyway, this radiation shows up as heat in the universe, and that heat is left over from the Big Bang. That super white hot explosion was an intense amount of heat, and the universe is still cooling off from that. So by detecting that cosmic background radiation, that's our evidence that a Big Bang event happened at one point. Thanks for watching.